Hi guys, welcome to Geo-Aakarshan. Myself Deepak Kumar. I'm a senior geoscientist and I'm working with AMGS. I'm based in Trondheim, Norway, and today I'm going to give a small talk on EM methods. Over here, I would be mostly talking about the marine application of EM in geophysics. And in the marine also we have quite number of application. So I would be focusing mostly on the control source electromagnetic, which is also called CSEM, and a little bit about the magnetotelluric, so which is empty data. Before moving into the main lecture, let's talk a little bit about the theory. So as you know that the EM methods are mostly different methods are different, but the CSEM and the empty data are mostly the low frequency technology, and they basically work on the principle of Maxwell equation, which describes the mutual interaction between the electric and magnetic field. And on this basis only, most of the EM application works, and so do the CSM. So let's. There are a range of EM application in the geophysics, starting from defense, archaeology, mining. In the mining, there are lot number of application which is used. Oil and gas. In the oil and gas, it's also used on the onshore and offshore. So we would be talking in today's talk mostly about the offshore, and then the groundwater, which one of the major technology that is been used in the groundwater is the EM technology, uh, which gives us the presence of the groundwater beneath the earth. Engineering, and also in the tectonics. So in today's talk, we would be focusing more on the EM application used in the oil and gas. Before talking about the different application, do you know why do we use EM in the oil and gas exploration? What is the basic fundamentals? The basic fundamental is that the oil and gas containing structure or the reservoir are characterized by very high resistivity, while the surrounding sea bottoms formation are filled with the salt water are very conductive. Therefore, the petroleum reservoir represent a clear target for the EM methods. Sorry. Um, and there are basically there are four techniques which are used in the um, marine environment for exploration of oil and gas. The first one is the magnetotelluric, which is also called MT. It is a very low technology. It's a very low frequency technology, and it utilizes the natural field. So there is no source. It's a passive source current is used over here. It's mostly used for the deeper investigation. The second one is the resistivity logging, which is, I mean, when you do the well logging, there are a number of lo logging data available like resistivity, sonic, gamma ray, density, and many more. So resistivity is one of the key tool which is used to interpret the oil and gas zone where the oil and gas or hydrocarbon are present. And then comes the control source electromagnetic. So the reason why I divided into two parts is that there is a two way of acquiring the data. One is the towed control source electromagnetic, which is much more suitable for the shallow water, and it's mostly the 2D technology, or you can say dense 2D 3D technology. And the second one is the control source electromagnetic, which is node-based control source electromagnetic survey. So over here, you deploy a lot of receiver on the sea floor, depending on type of the exploration you are doing, and then accordingly you decide the spacing between the receiver and the tow line, and you acquire the data, and then you invert the data and interpret it for presence of oil and gas. So before talking about the CSEM, what controls the resistivity in in the rock? On the left-hand side picture, let me turn it into the laser pointer. Yeah. So on the left-hand side picture, you can see that a well is getting drilled, and then we have the water column, and beneath we have the subsurface. In the subsurface, you can see there is a reservoir, which is half indicated with orange color, and the rest half is indicated with the sky blue color. And its whole is consist of a reservoir. And this orange color is the hydrocarbon, and beneath is the water. And when you look into the resistivity log, so there are different kind of logs. I'm not going to discuss about all the logs, but just a little bit about the resistivity log. So when you look into the resistivity log, you can see that where we have the hydrocarbon, presence of the hydrocarbon, the resistivity log shows the elevated response. Whereas if we have the water in the reservoir, then the resistivity log is showing very low or equivalent to the background uh, resistivity response. So why is that? The main reason for that is, if you look from the physics point of view, hydrocarbon are resistive, whereas saline water are conductive. So if there is a presence of the water and the hydrocarbon, and if you do the logging, the saline water will always give you a conductive response, whereas hydrocarbon will give you a resistive response. So when we will look into the resistivity of the water-bearing sediment, it generally falls from 1 to 2 ohm meter, depending on the mineral content and other stuff. It can also goes up to 4 5 ohm meter, depending on the background resistivity. Whereas if there is a presence of the hydrocarbon, it may go from 10 to 100 or more higher resistivity. The the resistivity of the hydrocarbon depends on couple of things, like what is the saturation. If saturation is high enough, then you'd be having that reservoir will be showing you more resistivity. If the saturation of that reservoir is low, let's assume that if it is in the saturation is in the range of 10 to 20%, then the resistivity will drop down to 8 or 10 or even lower. So let's Before going into the main lecture, let's look into the similarity between seismic and CSEM, um, or differences between the seismic and CSEM, especially in terms of the imaging resolution. So when we talk about the seismic works on the on the physical property of acoustic impedance, whereas CSEM, control source electromagnetic, works on the physical property of resistivity contrast. So if there is a resistivity contrast, then you would be able to get raised. And in the seismic, if there is acoustic, I mean, it works on the principle of acoustic impedance, which is density and velocity. So if there is a change in the acoustic impedance, you would be able to see the reflector in the seismic. When it comes to the seismic, it's more sensitive for the structure. So if you want to image a structure, or I should say, if you want to find the traps or the reservoir, its seismic is pretty good in giving that. So if you'll see, most of the dry wells are not because they are not able to find the reservoir or the traps. It's mostly because they are not able to find the charge, or you can say the fluid. So because of that, most of the dry wells, the wells get dry. Whereas CSEM is not really much more sensitive to the structure. I mean, especially the minor structure, but if there is some resistive structure like salt and basalt, to that it is sensitive to. But one thing to which it is pretty much sensitive is the fluid type. So it can differentiate between the resistive fluid and conductive fluid. And as per the physics, you know that salty water is conductive, which is a conductor, and hydrocarbons are resistor. So if you are acquiring CSEM, you'd be able to differentiate between the conductor and the resistor. In terms of the resolution, seismic have a very fine resolution, whereas the CSEM has very coarse resolution. And why is that? I will come back to it very soon. In terms of the velocity, both seismic as well as the CSEM have the same magnitude, which is approximately 2000 meter per second. And in terms of the frequency, seismic uses a bit higher frequency, which is from 3 to 80 hertz, whereas CSEM uses very low frequency from 0.05 to 5 hertz. And if we talk about the MT uses even more lower frequency. It goes to 0.0001 hertz or something like that. Another thing we talk about the fluid. I mean, CSM is sensitive to fluid, whereas seismic is not. Seismic is also sensitive to the fluid, but there is a difference. So if there is a fluid, then you would be able to see change in the acoustic impedance. But if we look in terms of the saturation, so if even 10% fluid is also present in terms of 10% saturated fluid is present in the area, then you would be able to find that change in the acoustic impedance. And the difference between the 20% saturation to 80% saturation, I mean, in acoustic impedance don't show much of the difference. So if your reservoir is charged with, let's say, 20% hydrocarbon saturation or 80% hydrocarbon saturation, you won't be able to differentiate that on the basis of the seismic. Which means that if you are drilling a well and if the remnants of the phase gas or remnants of the gas is there in any of the reservoir, you'd be able to see a change in the acoustic impedance, but you won't be able to confirm whether that would be commercial or not. When it comes to the CSEM, basically CSEM start giving you the register once your reservoir is charged more than 60%. Sorry, I mean once your reservoir have saturation more than 60%, then only you would be able to see the register. Else you would be able to see very fainted elevated resistivity. So that's one of the major difference. If you look over here on the left hand side of the slide, you can see that a lot of wells has been drilled in this area. This is an example from the Brazil. And on the basis of the seismic, they try to get a very nice AVO class in this region, and accordingly the prospect has been marked. But when they drill, there are a couple of dry wells and there are a couple of discovery wells. And what was the reason for that? It was the same reason that it was not basically 100% these wells are dry. I mean, you would be able to see some remnants or some low saturation hydrocarbon in these wells. But those hydrocarbon, the low saturation means that you won't be able to extract hydrocarbon from those reservoirs because there is no pressure in the reservoir and extracting. I mean, if you manage to extract also somehow, it won't be commercial because the volume would be quite less. So when we did the CSEM, we see a couple of register present in the area, and if you will see all the names in this map represent a discovery well, and all the wells without any name, they are basically dry wells, and you can see easily that they are sitting on the conductor. over here the red color represent to the resistor and the blue color represent to the conductor. So if you will see over here, it has been drilled on the conductor. This well has been drilled just on the edge of the prospect. This is drilled on the conductor. This is drilled on the conductor. This is drilled on the conductor. So if you want to save the well, then try to use another physical property in your interpretation. So use seismic, use CSEM, use more geophysical data. That will reduce the risk of your interpretation, and you would be able to get success in your interpretation. So when we talk about the CSEM, what is CSEM? CSEM is a geophysical method for remotely mapping subsurface resistivity. It can be used to map potential hydrocarbon accumulations such as oil, gas, hydrates. It can also identify the major change in the lithology that is affected by resistivity like basalt, salt, basement, and carbonate. Um, if you'll see in the center of the slide, there is an image and that represent the acquisition of CSEM data. So if you will see this uh, picture over here, this represent a multi-component EM-based receiver. So the reason for saying multi-component is that because it can record inline data as well as azimuth data. What is azimuth data? So azimuth data is that if you are towing on this line and the receiver sitting on the another line is also recording the data, which means that it is fulfilling the gap between the lines. So because we don't have a receiver between, so the azimuth data gives the information between the line. This is the transmitter. So basically, normally the length of the transmitter, what EMGS uses is 300 meter. It is towed 30 meter above the seabed and towed over the line. So first complete one line, second line, third line, and accordingly. And at the same time, when the receiver sits on the sea floor, they also record the empty data. Um, and the source for the empty data is the natural EM field generated by interaction of solar wind with the magnetosphere. That's basically a plane wave which goes beneath the earth and comes and get recorded into the receiver. When we talk about the and how much water column we can do the acquisition for the CSEM. So as of now, from 20 meter to 3,500 meter water column, in this much of depth, water column depth, CSEM data has already been acquired, and maybe going into the future, even more deeper acquisition can be done. But as of now, it is from 20 meter to 3,500 meter. Um, we will talk about the CSM sensitivity in upcoming slide, but just wanted to let you know that while we send the EM signal, it's get attenuated as it goes deeper and deeper. So it's not possible that we can image each and everything at a very deeper depth. So CSEM also has a limitation in terms of the depth. So it can, depending on the sensitivity, it can detect the reservoir from 0 meter to 4,000 meter below the mud line. Depending on if the reservoir is really elephant size, I mean quite big, then it also may have some response to the CSEM, but in most of the cases 4,000 meter is more than enough. When it comes to the empty sensitivity study, so as we drop the receiver, we also record the empty signal. So depending on the listening time and other stuff, you might be able to create the image up to 15 kilometer below the mud line using the empty data. So what are the places where we can use the CSEM, and in which sense? So definitely we can use the CSEM prior to the commitment. So if you are bidding for the block and if you wanted to do some commitment in that block, you can use the CSEM data. It will help you to identify the basin plate types or maybe the regional geology. You can also use it to um, identify the prospectivity of the block, or you can say block prospectivity evaluation, and definitely for technical programs, if you wish. Apart from that, it can be used to do the portfolio optimization. So let's say if you have 3 or 4 prospect in a block, um, and if you wanted to optimize that, which one to be drilled first and which one to be drilled last. So for that also you can use CSEM. Also in terms of the reserve or volume estimation, and to disqualify the non-commercial prospect. It can also be used in the well placement, which is one of the most important one. The reason being that drilling one well in the offshore cost a lot of money. So if one well goes dry, I mean, you lose a lot of money. So it can be used in the well placement to determine the fluid distribution, optimize the placement, validate the AVO, and definitely you don't need to drill the conductor, because if CSEM says there is a conductor and if you drill there, the chances for finding the hydrocarbon is very minimal. If you find it might be non-commercial, I mean it may have very low saturation or it may have very small volume which you may not be able to extract or make it commercial. The fourth one is the structural imaging. What is structural imaging? So it's when in the area if you have salt and basalt where the seismics basically fails to define the geometry of salt and basalt. That is something you can do pretty easily on the basis of the CSEM data, because salt and basalt are resistive in nature, and CSEM basically pick up the resistivity contrast. So if you want to see the salt and basalt in the area, you can easily use the CSEM and MT combination and use there. And last but not the least, you can also use it in the drilling hazard. So if in the area, if you have the high rates or something else, you can use the CSEM to avoid drilling those things and use it in a constructive way. Uh, so let's have a look into the marine CSEM workflow. So as I mentioned earlier, the first thing what we do is that we collect the information from the customer and then we try to do the sensitivity analysis. So there is a kind of a map over here where you can see, and you can estimate the sensitivity of the CSEM. So if anything falls in the pink one, you can say, okay, CSEM is not sensitive. And if anything falls in the green zone, you can say, okay, we are sensitive and CSEM would be able to pick this kind of response. Then basically we do the survey design. Why the survey design is important? If in the area, if you have a pipeline or wellhead or something else is going into the area, then basically we have to be very careful so that we should not hit those pipeline or the wellhead, because we use the node receiver and we drop it free fall on the seabed. So it's better to get all those information prior to the survey and design accordingly. If we have a pipeline in the area, then it's always useful to plan your survey perpendicular to the pipeline so that the response of the pipeline should be minimal in your data. Then definitely drop the receiver and and then to the transmitter and acquire the data. Once you get the data, you basically do the processing of the data. So we'll talk a bit more in detail um, how the data is acquired and how the data is converted. But then we do the processing of the data in the frequency domain. And then there are a couple of a mathematical technique which we use to create the resistivity cube. So just like the seismic, it's also the resistivity Segway cube so that you can blend together with the seismic and sorry, you can blend together with the seismic and you can do a joint interpretation. And once you have the inversion cube ready, you can do the interpretation and you can do the post inversion evaluation or interpretation where you can update the volume which has on the basis of the CSEM data. You can update the probability of success risk. So you can talk about okay whether it's the probability of success is going to be higher or lower. So you can, in general, companies works on the if anything is more having probability of more than 50%, then they take a chance and drill those prospects. But when you are using the CSEM data, you can make those P50 case, either P80, P90 case, or decrease it down to the P10, P20 case. So it would be much more easier for you to take the decision and you would be pretty much close to the, because on the basis of the CSEM, the lateral extent of the CSEM is pretty nice. So you would be able to tell which compartment of the reservoirs are charged with the hydrocarbon or filled with the hydrocarbon and which compartment of the reservoir is not filled with the hydrocarbon. So let's watch a video. Here you can see that receiver has been deployed on the sea surface and a current has transmitter passes the current. As soon as the current reaches the resistor, basically the guided wave gets partially refracted and get recorded into the receiver. And this is how the acquisition is done. So let's have a look into some of the example and see how the CSEM works. So this is one of the case study from Gulf of Mexico. This paper has been published. If anybody wanted to look into this paper, they can um, search on the Google. So basically in this region, there are two flat spots. One you can see with the red dotted line and the another one is with the white dotted line. So here, on the basis of the seismic noise AVO response to flat spot has been identified, and the customer over here wanted to drill. They were pretty happy that there's two flat spot and they are going to find really big reservoir in this region. And they drill it in the first well. They drill it in the center of the first flat spot, and they found discovery, and they really got excited. And then they acquired the CSEM data. And on the basis of the CSEM data, because CSEM data is really pretty good in defining the lateral extent of the reservoir. So on the basis of the CSEM data, we found that even the first flat spot is not fully charged with the hydrocarbon. And the second flat spot, everything is conductor basically. But customer wanted to drill in any case because they had some commitment for the well in this area. And they drill the appraisal well over here and the result was dry well. The first one was discovery well, which is matching quite nicely with the CSM response. But here we don't see any register, and when the customer drilled this well, they found this well as a dry well. So if you look, so on the right hand side top, you can see two map. One is the variance map, and the second one is the variance map overlain with the CSM response. And this you can see that there is nice response of the seismic and a small response from the CSEM. So, and below you can see the vertical section of this area. So we try to take a vertical section passing through both the wells. And in the if you look into the appraisal well, there, I mean, there is no, this is a resistivity log, and there is no elevated response in the resistivity. But if you will see this well over here, you can see a nice elevated response of the in the resistivity log. At the same time, in the CSEM, you can see nice register sitting over here, but in this near to this well, there is no register, which confirms that that only this small white polygon is charged with the hydrocarbon, and the second polygon, the flat spot, might be due to any other region. So if you remember, initially I talked about when CSM start giving you the response. So if you have more than 60% of saturation, then only you see the CSM register. But when it comes to the seismic, basically anything above 10 to 15% of saturation can give you same kind of seismic response, and it doesn't differentiate between 20% saturation and 90% saturation. So basically it would be more or less the same response, and that's what happened in this case. So this is the and this small saturation can come from the feed gas or something else like that. And this is what happened over here in this case. So this was having very low saturation phase gas, which turns the response of the seismic. But for in case of the CSEM, definitely until unless you don't have really high saturation, CSEM won't be able to pick those prospects. So in this case, the first flat spot is charged with the hydrocarbon, but not the second one. Um, So definitely after doing the CSEM, we also try to risk the prospect, that how it goes. So we plotted the prospect over here, and the P50 case and the probability of success. And after doing the CSEM, basically we came to know that okay, the outer area is not charged, so we reduce the volume, but we increase the probability of success. Apart from that, only register, I mean, we don't really need to look into the register only. We also can look into the conductors, because if you have identified some structure or some nice AVO response, and if that's matching with the conductor, then it's a good way to decide that we should not drill those prospects and save the wells, uh, which is a lot of money. So let's have a look into another example, which is from Southeast Asia. It's a deep water prospect, and the block name is it's in the Malaysia SK2C, and the prospect name is Paus Prospect. So there was a small prospect in this area, and you can see there are two wells drilled in this region. EM just acquired two 2D line in this area. The reason being that customer was acquired the seismic, and you can see the seismic was totally wiped out. There was nothing over here, which is a good sign. The reason being that this kind of seismic wipeout you are able to see because of the gas chimney. It means that if there is a gas chimney, there would be some potential hydrocarbon reservoir in this region. But the problem is that if seismic has been wiped out, how you are going to point out where the prospect is. But customer drilled two of the wells. One of the well was something over here, and one was dry, but second one was sorry, this one was discovery, and this one was dry. So they asked us to do the CSM. Acquired the CSM data in this area. So we basically acquired two 2D lines in this area, and you can see that although because as CSM is not sensitive to the phase gas, so CSM is not giving register everywhere. It's just giving the register where you have the high saturation hydrocarbon present. So we try to plot these two lines. So one, this is the called post 01, which is this line, and post north 01, which is this line. So post north 01 is this one, and here we have one well, which is this one over here, and we can see no elevated response in the resistivity. And apart from that, CSEM also gives a conductor at this location. But when we looked into this line over here, POS 01, which is this line over here, and this is the second well is setting something over here at this point, and you can see elevated response in the well log, the resistivity log, and when we inverted the data, we are able to see some another register sitting over here. Apart from that, we are also able to see second register, which we don't know exactly whether this is connected to this one or not, because it's a 2D line. So in between the line, it's mm, quite tough to get the information. But because of the broadside data is still up to certain distance, the registers are confirmed. But whether it is connected or disconnected, it's for that you definitely have to acquire the 3D data. But the good thing is that where the seismic wipeout was there, I mean, CSM gives you some nice register, and that's associated with the hydrocarbon. So that was the example where you can use the EM in uh, prospectivity or finding the oil and gas. But apart from that, you can also use CSEM and MT. MT is the magnetotelluric to do the define the geometry of the structure like salt and basalt. So this is one of the example multi-client data acquired in west of Setland, and you can see there are group small 3D survey done, and these two small 3D survey joined with one 2D line. And in below you can see the seismic data, so you are able to see the top of the basalt pretty nicely. But when we talk about the base of the basalt, nothing is clear. I mean, it's quite tough to predict the base of the basalt just on the basis of the seismic. So uh, data was inverted. On the left hand side top you can see the CSM inversion alone, and in the bottom you can see empty data alone. As CSM data is sensitive to the register and empty data is sensitive to the conductor, so accordingly you can see the response. Uh, if you will see where the basalt is thinner, where their CSEM data is working pretty nicely. But as soon as basalt is getting thicker, I mean CSEM data also start losing the sensitivity. And to get more sensitivity, then what we did that we do a joint inversion of CSEM plus MT. And when we do the joint inversion here on the right hand side, you can see the picture what we got from the joint inversion. And now the even the thick basalt or the thin basalt, both has been mapped or imaged quite nicely. And not only that, because of the empty data, we also start seeing the basement, which has been imaged pretty nicely. Um, so we try to correlate the same stuff. So on the left hand side top over here, you can see it's a seismic where it was quite tough to see the stuff. And then this is the CSEM data, which is matching pretty nicely when basalt is thin, but when basalt is getting thicker up to 2 km, then it started losing the sensitivity. And in the MT, basically, I mean, MT is more sensitive to the conductor, so it's alone MT is also not able to explain this. But when you join the CSEM and MT together, then you can see the basalt has been imaged pretty nicely. And this is the seismic section, so only a small area seismic section was available with us while doing this study. So it has been imaged quite nicely, and it gives us a very good result. Yeah, so that was all, I think, from my side. The last thing, just wanted to let you know that how you can achieve the best result when you are using the CSM data. The first thing first, that you have to learn how to enhance your existing workflow. So when you are working as an interpreter, you need to incorporate more and more data, seismic, CSEM, gravity, magnetic. So more and more data you have, your interpretation risk is reduced accordingly. Um, then you have to definitely incorporate the result into the geological evaluation. So if, as I mentioned, every additional independent Earth property provides additional insight. So more the data you add to your interpretation, you will reduce the risk, and that's what we want in our interpretation, right? Apart from that, you can also use the CSM data to do the reserve estimation, determine and update the probability of success. And definitely in the last term, you can take a decision of drilling a well or saving the well cost, because in the offshore, the well cost is really pretty high. So yes and no decision. This is all from my side. I hope you enjoyed my presentation. Thank you very much. Thanks for your time. Cheers. Bye bye.